Hi everyone, in this video we're going to talk about strong acids and weak acids. To start, we're going to look at the definition of strong acids first. Basically, strong acid is defined as the acid that is completely dissociated in aqueous solution. This is the characteristic of a strong acid. The keyword that you need to remember is completely dissociated in aqueous solution. Remember, in the previous video, we have talked about what does it mean by aqueous solution. It simply means that when you have a strong acid, you put that into water solvent, it will be completely dissociated to form ionic products. Let's have a look at a few examples over here. We have three examples of strong acids. So let's have a look at the first one, the most common one, HCl, hydrochloric acid. In brackets, you see here, it is already in aqueous solutions, means they are dissolved in water. So because they are completely dissociated, the equation will be using a reversible arrow. This is because your HCl will be 100% or nearly 100% dissociated, changed into H plus, your proton, and also the chloride ion. So we can say that at the end of the reaction, we are no longer having HCl in the system because all of it will be dissociated and to form your ionic species right here, H plus, proton, and chlorine minus in aqueous solution. Aqueous right there simply means that the ionic species are dissolved in water solvent. Now let's have a look at the second one. We have talked about writing the equation for acids and base. For acids, you can write it in this form, or if you want, you can also include water liquids here. If I like, I can also write plus H2O liquid. And this time, if we have water liquid written in your equation, if you prefer to do this, it is still going to be completely dissociated because it is a strong acid. But this time, instead of writing your proton, we're going to write your hydroxonium ion H3O plus. So we're going to have H3O plus in aqueous. This HNO3 will be dissociated completely, and the H right there will be donated to your water molecule to form H3O plus. Right now, instead of liquid phase, it will be in aqueous because it's no longer in liquid form. It will be in dissolve in the aqueous solution. Okay, and also we're gonna have NO3 minus aqueous. Same goes to this, so you can have two options, whether you want to write it in this form or you want to have it written in this form. It's really up to you. So I'm going to use the one on top because that one is simpler. Still, it will be using a reversible arrow because this is complete dissociation. Strong acid will be completely dissociated to form your ionic species, to form this. This is very important. This is the reason why you are acidic, because you're able to give away H plus according to Arrhenius theory. Arrhenius theory says that acids is the species that will be able to produce H plus to the system. And we're going to have H SO4 minus, don't forget your phase. So these are the examples of how you're going to write the chemical reactions for strong acids. Remember, guys, always remember, every single time if you see arrow like this is being used, that is the indication your acid is a strong acid. A piece of information that I can give to you for strong acids is most of the inorganic acids that we have, like HCl, HNO3, H2SO4, H3PO4, those are considered as strong acids. Now, what about weak acids? Weak acids is defined as the acid that will be partially dissociated in aqueous solution. So instead of fully dissociated in aqueous solution, for weak acids, they will be partially. Partially over here means not completely dissociated in aqueous solution. When you have partial dissociation for weak acid, let's consider these weak acids here. These are some examples of weak acids. They will be partially dissociated in aqueous solution. So when you have partial dissociation, so instead of using irreversible arrow, we have to use reversible arrow because weak acids will achieve equilibrium. The reason is because they are partially dissociated. This is your weak acid, and we're going to use reversible arrow, and it will still going to be producing the same proton, and that proton will leave the compound over here, and you're going to form this negative charge species. The only difference that we can see between weak and strong acids is the use of arrow. For weak acids, if you want to write the chemical equation, we're going to use reversible arrow because they will achieve equilibrium. What about this? So let's say if I'm going to use water, I'm going to write water here. Still the same concept. It will be in liquid. HF is another example of a weak acid. And you're going to be forming H3O plus aqueous plus F minus aqueous. It looks very similar to what we have done for strong acid just now. The only difference over here at this point that we can observe is the utilization of reversible arrow for weak acid. Remember why? Because they will achieve equilibrium. So, since weak acids exist in equilibrium, they can have Ka value. Okay? So Ka right here has the same concept as what we have learned in Kc, and Kp in the previous chapter, chemical equilibrium. If you know how to write the expression for Ka, Kp, and Kc, you should be able to write the expression for Ka. The reason why weak acids will be able to have Ka, because they will exist at equilibrium. The reason why they can have equilibrium, because they are partially dissociated in aqueous solution. So, Ka is defined as the acid dissociation constant. And let's have a look at one example over here on how to write the Ka for this. So we have the Ka. A over here stands for acid, okay? Acid dissociation constant. That is the product. So we're going to write that in terms of concentration. So you're going to have in brackets, still the same as what we have done before, to the power of 1. And then H plus, also to the power of 1. Divide by your reactant, CH3COOH, to the power of 1 right here. So this is how you're going to write the Ka for this dissociation of weak acids.